Hey guys, STAT1800. Starting simple linear regression. You might say, well, why are we starting it? We did it last week. Now we're really starting it this week. We're starting the, I would call the big boy, big girl, simple linear regression stuff. Um, I'm just going to go ahead and tell you some of the stuff that we're going to do is going to seem redundant to you. And you might say, well, some of the stuff you've already done has been redundant anyway, so I'm used to it. But I think you're even going to find out more so in this video because I'm going to show you multiple ways to essentially come up with the same answer. And, as a student, that's one thing I say all the time is, to get to my position and be able to do what I do, I had to be a student for many, many, many years. So I know what it's like to be a student, and I think as a student, it's going to be natural for you to think, well, why is he showing us all these different approaches? Well, guys, the reason I'm showing you a lot of different approaches is because right now we're doing simple linear regression, and ultimately we're moving into multiple regression, where we have multiple predictors. So we need a tool bag with a variety of approaches. So, once we get there, we'll because ultimately what we have one kind of model diagnostics where we look at the effectiveness of our model in predicting, whatever dependent variable we're interested in predicting. But we're also interested in the individual predictors. So when you're in the simple linear regression case where you have just one predictor, these things do seem redundant. So guys, just trust me. I'm not going to put you through a bunch of stuff that isn't needed. So, guys, at the end of the day, what I hope that you've taken away from the previous videos is we're studying correlation and regression, and the purpose is to examine the relationship between two quantitative variables. All right, and the procedure that I want you to think about in the simplest case is I would first of all want to look at a graph, and the graph that we look at in this case is a scatter plot. So we look at the relationship between x and y, and if we have something that kind of takes on a linear pattern, then correlation regression is the tool for you. If we end up with something that's, not necessarily gives us a linear pattern, more of a curved pattern, then this linear regression is not the tool for you. Now, there are statistical techniques that we can use to create a model here to predict y from x, but this linear regression doesn't apply there. The second thing that I would want you to do once you establish from the picture that a linear relationship does exist is to examine the correlation. And there's two parts to correlation that I want you to consider, R and R squared. R is the correlation coefficient, R squared is the coefficient of determination. We're going to study this a lot more, so I'm not going to go into that a lot. And the third thing I want you to do is to think about regression. Regression is just an additional technique that we can use to describe the relationship between x and y by fitting a linear regression model to our data. Now, the simple linear regression model guys, simple linear regression, when you see simple linear regression, you should think that we have one predictor. Okay? So the simple linear regression model is y sub I, our dependent variable, can be expressed as our intercept plus our slope times the x value plus an error term. So to take an x value and make it equal to the actual or the observed y variable, we're going to have actually an error term. Guys, let me make this a little clearer. Hopefully that helps a little bit. Now, this part right here is referred to as our model. And if we remove the error term, then we have the predicted value given as b0 plus b1 times x sub I. So we can use our model that we create, insert the x value that we collected, and actually get a predicted value for this particular x sub I. So again, this is a prediction model. This is the overall model. Now, what we use here is we use these beta zeros and beta ones. I want you to think of those kind of as mu's and, well, we use pi's, don't we? Mu and pi. And, you know, if we have an unknown value for mu, we're going to collect a sample mean, x bar, to estimate mu. If we have an unknown proportion or unknown percentage, then we're going to use a sample proportion to estimate that. Well, that's what we're doing here, is we take a sample intercept to estimate the model intercept, the population intercept, and we take a sample slope to estimate the population slope. So this is the population intercept. This is the population slope. So we're ultimately, guys, we have some x value that we are using to predict a y value. We take a simple random sample, and we use a simple random sample to try to estimate the model that describes the relationship between x and y for the population. So we might, for example, want to take, see how predictive ACTs are of first-year college GPAs. So our model would be y equals beta 0 plus beta 1 x sub I plus an error term. So we would have y, which is our first-year college GPA, equal the population intercept plus the population slope times the x value, which is ACT, plus the error term. But guys, typically what we do is we collect a random sample of first-year GPAs and ACTs, and we use our sample model for prediction. So we can predict from our our intercept plus our sample slope times the ACT. So guys, it's important that you realize that when we spit all this information into StatCrunch or even calculate it by hand, that the B0 that we get from our model, the intercept, is an estimate of the population intercept. The sample slope is an estimate of the population slope. So these together create an estimate of what this model is that describes the relationship between all ACTs and all first-year college GPAs, obviously across each individual. Where this model right here is created from our sample that we collected at random from the larger population. So, in teaching this in this subject, at the undergrad level and at the graduate level, I found out that graduate students as well as undergraduate students have a hard time understanding that there's this larger unknown equation, this model that we're trying to predict, and we use this to actually make these predictions. Now, ultimately, guys, what's going on here is we use something, and you'll hear me say this a lot. Use something called least squares. And if we take this y sub I equals beta 0 plus beta 1 x sub I plus our error term, and then we take y sub I to be our beta 0 plus our beta 1 x sub I, we can examine what the sum from I equal 1 to n of our y sub i's minus our y hats quantity squared would look like. And these things are called the sum of squared differences. Now, the goal in this least squares approach is to minimize the sum of squares. And it's one of the reasons that we call the model that we actually end up with the least squares model. Some people call it the line of best fit. So anyway, guys, what happens is we've got our data here. And essentially, what does this difference tell us? This difference tells us that we're examining the difference between the actual value and the predicted value. So we come in and we create a line. Let's just say that we create this one right here. Well, when I come into this x value right here, my predicted value is this. The difference between the actual value and the predicted value, so I've got another x right here where I have a predicted value. You can see that those distances is going to be quite a bit because this line is a long way from the central focus of our data that we've collected. In fact, I may call this the line of worst fit. It's horribly. It doesn't fit the model well at all because our predicted values are so far away from our actual values. But guys, there exists one unique line that goes down through the central focus of our data that we've collected, where let's just take this as one of our x's right here, so this is an x right here, where our predicted value and our observed value for each of these x's is minimized. So if I sum this up, plus this up, plus this up, plus this up, plus this up, looking at the difference between the observed values and the predicted, there's some line that exists that would create the least sum, the smallest value of the sum of all those distances. Clearly, guys, this isn't going to be it because this is a long way, right? From the predicted to the observed. All these go from the predicted all the way up to the observed. Again, this is like almost the line of worst fit, although it's not, because you can continue to get worse by moving the line further and further and further away from the central focus of our data. So again, guys, minimizing the sum of squares finds the unique linear model that we call the least squares regression model. All right, so that probably is a little bit more theory than most people like to get. So let's kind of shift gears from the theory to something that we get more in terms of practice, and that is something we call a residual. Now, I covered this in one of the previous videos, but we're going to get into it a lot more in a lot more depth in these videos right here. So, guys, a residual analysis is essentially the well, let's just create a. It's the observed y value minus the predicted y. So let's just say that we've got some values here, and let's say we have some values between x and y, and we have 1, 3, 7, and 2, 10, 15. So guys, if I was going to create the linear regression model from this very quickly, I would have y hat equals some value plus another value times x sub I. This is clearly called our slope. I'm sorry. This is clearly called our intercept. And this is clearly called our slope. So B0 and B1 respectively are our intercept and our slope. So guys, what I would do is I would put this into some sort of technology, and I would probably go to my math lab, sign in. All right, one of my graduate students has been using all right, go to StatCrunch, and I would go just to the website, and I would type in my data. So guys, I would go up here and just call that X, and I would just go up and call that one Y. So again, very quickly, I can go 1, 3, 7, and I can go 2, 10, and 15. So guys, I can go to regression, simple linear regression. I want to use X to predict Y. I don't want to do any fancy stuff yet because I haven't shown you that kind of stuff yet. I'm going to save the residuals, and I'm going to go compute. So guys, under estimate, I can see that my intercept is 1.5. Dropped my pencil. So 1.536. And my slope is 2.036. Now, something you see kind of cool is these residuals have been saved in an additional column. Now, by the time this week's over, you're going to learn far more than you really ever cared to know. You're going to learn about sum of squares for your regression, your error term, your total, how we get the f-stat, what it means from the p-value. Here is less than 0.05 or greater than 0.05, and we're also going to learn all sorts of stuff about this table. But what we can see is we have a correlation coefficient of 0.95, but more importantly, we can see that our model, at least more importantly right now, we can see that our model is easily found by this right here. All right, and we can go on to the right, and we can see that our fitted line, that least squares regression line, that minimizes the distance between the observed and the predicted, the observed, the predicted, and the observed and the predicted. There is no line that exists that the sum of these values right here, these distances, is smaller. This line created the smallest sum of squares. All right, gang, so let's go back over to this and examine more about a residual. So how do we calculate a residual for the first? Well, guys, remember, a residual is the observed y minus the predicted y. So it's the y minus the y hat. So our observed y for the first observation is 2. And the predicted y is found by putting our x value into the model, and putting the x value in there. So again, y hat is found by taking the intercept plus the slope times the x value. So x value here is 1. So guys, put that into your calculator very quickly. We get 2 minus 1.536 plus 2.036 times 1. And we get negative 1.572. Well, we kind of already knew that, didn't we? Already kind of knew that because right back here, a little bit of rounding issue there. This gives us negative 1.571. But keep in mind that this residual is a better approximation because it used the entire decimal expansion. So if you go back to the results, you'll see that the slope was actually 2.0357143. I rounded it off to 3 places. If I had gone 4 places and 5 places and even 6 places, my residual would have come closer to the exact value that you see there. Well, guys, that's about all I want to accomplish in this video. The next video is going to get a little bit insane, but it'll work. It'll all work out in the end. So take care.